Yeah. Okay. Well, we're very happy to have Agustin Moreno visiting us from Heidelberg, going to tell us about a Poincare-Birkhoff theorem for C0-Hamiltonian maps with applications to the three-body problem. Hopefully.
Okay, thanks for the introduction and the invitation. Of course, it's always great to be back here at the great IAS and see so many old and new
You should
faces.
unmute yourself on Zoom.
I think it's.
Oh, no, it's fine. You don't have to.
Yeah.
Oh, okay. Oh, no, it's probably the room light that's picking it up for Zoom.
Okay, anyways, so. Yeah.
If anybody's watching and can't hear it, then they'll complain eventually. So.
Yeah, can see.
Okay. Oh, yeah, you should share your screen on Zoom, your slides. That work? Or sorry, maybe. Look.
There you go, secretive.
Is this fair? I guess not.
Okay, I think it seems that if you do the thing on Zoom, then it switches to Zoom and then we can't see it. So I think we should take priority. Yes, sorry, clearly I'm not great with the text.
It's fine. I'm also. And so today I'll talk a bit about sort of generalization of a very classical result. So the Poincare-Birkhoff theorem, in a setting that naturally arises in the study of celestial mechanics and the study of the three-body problem.
Well, yeah, three-body problem, got it. Solve all three-body.
One day, maybe. And everything that I'll say today is or will be included in my book that I just wrote and hopefully will be published by Springer when the referees come back saying how great it is. Okay.
That can take many years.
Yeah, well, it's out of my hands.
You can't see. You want to see it.
Okay, so and everything that I'll say, I mean, it's based on previous work with Otto van Kurt, who's in Seoul, and then my student Arthur in Heidelberg. Okay, this is not working. Now it's working.
Okay, cool.
Okay, so before I sort of tell you about that result and it's roughly speaking how it's proved, let me just go to the original problem, the restricted three-body problem. So this is the setup where we have three objects, which I will call the Earth, the Moon, and the satellite. They have certain associated masses, and then we just leave them to interact with each other according to Newton's second law of motion. So this gives us a very complicated dynamical system, one of the very early problems in dynamical system, really. And there's some classical assumptions that people have made to simplify the situation or consider the special cases. The first condition that we will assume is that the satellite is negligible when we compare it to the other two, which are called the primaries. So this is a restricted three-body problem. The second assumption, which is an approximation of the real scenario, is the circular assumption. We assume that the Earth and the Moon, they move in circles around their center of mass, as opposed to ellipses, which is the general case, the two-body problem. Most of the restricted three-body systems in the solar system are roughly circular. Okay, so this is not a terrible approximation. And then the planar case is when we assume that the satellite moves in the plane.
Satellite moves on purple.
The satellite can move in.
Yeah, not circular.
Right. Right. You care about the dynamics of a satellite. You fix the other two and then just study that one. So the planar case is when you assume that the satellite moves in the plane. That's the planar restricted three-body problem. That's the case always studied by Poincare, for example. And then the spatial case is when you drop that assumption and you allow the satellite to move in R3. So this is a high dimensional problem. And this is the one that we will be interested in. So this is the goal is to study the motion of S under the influence of the primaries. Very, very classical system. This is, of course, a Hamiltonian system. It's described by a fairly explicit and very simple Hamiltonian function. So because we assume that it's the primaries move in circles, we can sort of go to a rotating frame in which you're fixed. So you fix the position of the Earth and the Moon, and position say mu 0, 0 and -1 plus mu 0, 0. Here mu is a mass parameter, and Hamiltonian in this coordinate is actually time independent. Okay? So therefore, you have conservation of energy. You can fix the energy and study the corresponding dynamics in the level set. So the Hamiltonian is very simple. So you have this the kinetic energy, so representing free motion. Then you have one gravitational potential for each of the primaries. So this is what makes the Hamiltonian singular. And then the price that you pay is because of this rotating frame is this angular momentum term here. Okay, so before it wasn't, but before it depended on time. So when I change coordinates, I have this term appearing. Here we assume that the sum of the masses of the Earth and the Moon is 1. So this mu parameter, which is usually called the mass ratio, you can think of it as the mass of the Moon. Okay, so that's one of the parameters in the Hamiltonian. The planar problem is you drop the last two coordinates. So P3 equals Q3 equals 0. So you're lying in the plane. So this is by the physics, or if you want, by the Hamiltonian itself, it's a flow invariant subset. So it's a codimension 2 invariant subproblem. Okay? The planar problem sitting inside the spatial problem. So the two parameters, one of them is mu, and then the second parameter is the Jacobi constant, which I will think of as the value of the energy. Okay, so I fix, usually you fix mu, so therefore you're fixing your system. For example, the mu corresponding to the Earth Moon, which is of the order of 10 to the -2, and then you vary the other parameter, which is the energy.
In this, you remind me that Ziegel and Loza, they have a big deal that Earth, the Moon, and the Sun can't collide in the same spot.
Right.
So surely already that's built in with your E. And so are they looking at a more general thing?
Yeah. So in this case, you cannot have triple collisions, for example.
Right, that's forced there already.
Exactly.
That's a theorem that I remember that Ziegel was quite proud of.
Yeah.
Or at least was of.
Yeah, true. So in this case, in particular case, when you could only have binary collisions, so the satellite with the Earth or the Moon, and those are fairly easy to regularize. For triple collisions, you still can regularize, but it's much more complicated. So the Hamiltonian has 5 critical points called the Lagranges, L1 up to L5. These were found by Euler and Lagrange more than 200 years ago. Here in the picture, I am sort of graphing the value of the energies for different critical values. So here the horizontal axis is the mu axis, the vertical axis is the energy axis. So for example, here H of L1 is the lowest critical value of the energy, and it has this behavior. There's of course some symmetry with respect to mu equals 1/2, because the Hamiltonian is symmetric. L2 and L3 come later, and then L4 and L5 always have the same energy. Everything that's below L1 or slightly above, I will usually call the low energy range. Okay, so that's the range of energies where we will be able to do some contact geometry. Mu equals 0 is this axis here, which is called the rotating Kepler problem. So it's a two-body problem, but we'll remember we're in a rotating frame. So it's an integrable system, so you can study it explicitly.
It's the two-body problem because the Earth has mass 0. Or
The moon has mass. The moon is gone, so you only have the Earth, but you still have the angular momentum term. So it's not everything is periodic.
Oh, it's not.
No, I mean because the periodic orbits correspond to the period of the ellipse being a rational multiple of the period of the system, which is 2 pi. So you have some resonance condition to be periodic.
Oh, so is
It's
it
integral.
That's an integral system.
Oh, okay. So the energy surfaces are all boundaries of 40 ellipsoids or something.
You should more think of it like it's an integrable system where the frequencies in the Liouville tori are basically depend on how many times you rotate around the. I can tell you. Anyway, so this is a very easy system, so you can write down everything now. Okay, and then the range of energies in which we'll be interested, this low energy range, has the following topology. So for C below L1, so subcritical energy, if you look at the energy level sets, sigma C, they have three connected components. So one which projects down to a neighborhood of the Earth. So here, this is the position space, and the vertical direction is the momentum space. So if you project down, you see this neighborhood of the Earth, neighborhood of the Moon, and then there's an unbounded component to the energy level set, which sort of extends all the way to infinity. So this says that if you start with near the Earth and you have energy below L1, you will stay always near the Earth. You're like a Elon Musk satellite. Okay.
Mentions in South Africa.
The sense here near the Moon, right? If you go to a mission and you use a halo orbit, for example, you will stay always near the Moon. And if you don't have enough energy, you start very far away. You're one of the good asteroids, the asteroids that don't come to the Earth.
What had Hill, I assume it's Hill, the Hill from.
Yeah.
What had his regions he found for what purpose?
He was studying stability.
It's restricted.
Yeah. So this thing is called Hill stability. Basically, it's just classically allowed regions of motion. So he was the first one to consider them and study them. In the case of the Moon, so there's this corresponding Hill lunar problem, which is like a deformation or perturbation of the rotating Kuiper problem. But it's a non-integrable system, and in there he studied this corresponding regions. Okay, so there's this unbounded component which I won't be interested in. I will be interested in near primary dynamics, so low energy near primary dynamics. That means dynamics near the Earth, near the Moon, and below L1. So when you cross L1, you see that there's like in Morse theory, right? This is a critical point of index 1, so there's a handle attachment topologically that happens. So you see this transfer region. So in principle, you added enough energy to your satellite to go from the Earth to the Moon. Okay, and topologically, the corresponding level set becomes a connected sum. But it's still non-compact, right? So the non-compactness is due to collision. Remember that the Hamiltonian is singular at collision, so potential energy explodes. And this is a topological picture. I wouldn't show this to an engineer, right? They would be like, this is the actual picture that you should show to an engineer, right? So this is the level sets of a potential. So here you see the Earth here, say here's the Moon, and then you see the corresponding sort of Hill region. So above L1, you see this transfer region here in between. So L1, L2, and L3 are all collinear, so those are the Euler configurations. And then L4 and L5 are symmetric with respect to the x-axis, and they form the vertices of an equilateral triangle with the primaries. Okay, so those were found by Lagrange. Okay, those are very important. So because this L4 and L5 are stable, so usually you find plenty of asteroids, say in the Earth, Moon, three-body system, sort of lying around L4 and L5. So if you want something to stay there forever, if you want to put a telescope, usually those are the Lagrange points considered. The other ones are unstable. So. Anyway, so remember the Hamiltonian is singular at collision. So if the satellite crashes with the Earth or the Moon, then because of conservation of energy, the velocity needs to explode to infinity. So as in the picture before, the level sets are non-compact. This, for an engineer, of course, this is a tragedy, right? You don't want to lose your multi-million-dollar satellite. But we as mathematicians, we don't really care too much. So we have ways of dealing with collisions. So we do a very sort of naive thing. So when the satellite is crashing or going to crash against the Earth, you add a trampoline, so you slow it down. So now it becomes zero velocity, and when it collides, it comes back from where it came from. So you see this bouncing back trampoline behavior. So you can continue the dynamics. Before the dynamics was game over, now you can continue playing my dynamical system.
So it has some advantage of slingshots.
Right, exactly. So I was going to say that actually. So of course, collision orbits are not, it's a crazy mathematical thing to do, but then it turns out usually that if they're non-degenerate, you can always perturb them, right? And actually find actual orbits which go very close to the planet. And those are actually very useful for slingshots or gravity assist. So you want to get to a planet very far, you use an intermediate planet. So you do a slingshot along the planet to get a lot of momentum for cheap. So you only use gravity and you don't use fuel. That's sort of crucial for mission design.
I have a very vague question, which is how does is this construction at all like the real blow-up construction?
Yeah.
I mean, if I have a vector field going into a singular point, I can just look at the tangent vector.
Exactly.
Which hits the singular point.
Yeah, so the modular regularization works like that. So let me just explain now. So one of the ways that you can deal with with collisions is by Moses' recipe. There's also Levi-Civita's recipe. So this works as follows. So you first take your QP coordinates and you switch them. Now sort of the P becomes a Q, but you put a minus sign to preserve the symplectic form. And now you take the inverse of the stereographic projection. So you basically add a point at infinity. So you compactify the P's by adding P equals infinity. So now you have new coordinates and T star is 3. So you have to add sort of the collision, right? So P equals infinity is exactly the collision locus. So topologically this looks like this. Basically, as you said, it's like you're basically doing a real blow up. So you're adding all the infinitesimal directions in which you can collide with the Earth, say, and that's a sphere of directions. And you see it here. So, for example, you have to do this transformation, but also there's a regularized Hamiltonian which you need to write down. There's some formulas that I'm not writing down, but you can sort of multiply the original Hamiltonian by some function and then add some other. And then that's a regularization, and the property set, the level set now becomes compactified. So first of all, the zero energy level set corresponding to the regularized Hamiltonian is a compactification of the original level set. So it becomes S3 times S2, so it's a 5-dimensional manifold. And the dynamics here is a reparameterization of the original dynamics. Hamiltonian vector field of Q is a reparameterization of the Hamiltonian vector field of H. Away from collision, and then at collision is just a compactification. So topologically, topologically, what you see is this 3-dimensional sphere, which you think this is where P is moving. So I add P equals infinity, which is like the North Pole. That's the collision locus. And when I fix the energy, I'm taking a level set here in the fiber at the collision locus is a 2-dimensional sphere corresponding to fixed energy and all this directions in which I can crash against the Earth. So that's sort of what's going on basically. So the level set gets now, it's very nice sort of compact manifold. And here you see this S2, which also goes through infinity, is the planar problem. So the planar problem also has collision, so you have to also make it go through the North Pole. So this is a 2-dimensional sphere. So symplectically, it's actually this is the cotangent fiber, the collision locus. So it's a Lagrangian. And the 2-dimensional sphere, when you fix the energy, is the Lagrangian in the corresponding levels. That's sort of like the symplectic geometry of the situation. And the planar problem is, of course, like an invariant system. So this is sort of what we will be interested in from now on, like looking at this picture.
Okay, so this takes advantage of the fact that the momentum has to blow up as you hit the singularity.
Yeah.
Because if you just did a very naive real blow up, you would be compactifying by adding, an S5 or something. But here I think you add something much smaller. You add some S2.
Right. I mean, you still preserve the bundle composition. Yeah. You swap P and Q. So now Q moves on the fiber. So this is a 2-dimensional sphere of positions. Whereas P moves on the base, but sort of P explosion is exactly there. So now, of course, I mean, you regularize the dynamics of you somehow this is like a homogeneous way to view all the collision orbits. The collision orbits are now normal orbits. So if you want to sort of exclude that, you need to remember that you added collision at infinity. Okay. And let me say sort of a theorem which is due to Peter Alvarez, Frauenfelder, Otto, and Patterson for the planar case, and then Cho Young Kim for the spatial case. So what these people do is basically they show that when you compactify these level sets, they are not only compact manifolds, but they come with some geometry. They come with the contact structure. So the statement is you look at the corresponding bounded energy components for below L1 and near the Earth and near the Moon, or slightly above. And when you have a set, it not only is a S3 times S2 as a manifold, but it comes with a standard contact structure if you're below L1. So this is the spatial version. There's also a corresponding planar version when you replace S2 by S3 by S2. So these are cotangent bundles that have standard, standard geometries, standard contact structures. So the point of this theorem is now the rate flow that you started, the flow that you started with, you can view it as a rate flow. So now you have techniques to study rate flows. Let's try to deploy them. So this is something, the message of this. In all the cases, the planar problem, which we knew from before is an invariant subset, is actually a codimension 2 contact submanifold, which is invariant under the rate flow. That just means that the contact structure for the planar problem is a restriction of the contact structure for the spatial problem to the planar problem. Okay, so the geometry is sort of it's a sub geometry of the ambient geometry, but it's also a sub dynamical system of the corresponding ambient dynamical system. So the dynamics and the geometry sort of very nice and interact along the planar. Okay, so this is sort of opens up the
What does
game.
KAM tell you?
Well,
I mean, after all, you have the two-body
yeah.
integral, and this is perturbation of that. Do you have invariant? So I
Yeah.
guess you'll start showing us something.
Yeah, so I mean, if you think in terms of Arnold Deville coordinates for the integrable case, you have the integrable case along this sub-problem, along this codimension 2 thing, and then you have the integrable case in the ambient problem. So you add an extra 2 dimensions. So the tori are basically tori in the planar problem plus an extra dimension.
I guess when I'm trying to guess what you're going to be telling us about this dynamics, so I'm expecting there to be a lot of invariant stuff that's still there.
Yeah, for sure. But now you have a very nice decomposition between spatial versus planar. So this is going in the direction of trying to understand what's the geometry, sort of differentiating the planar from the spatial problem, and then try to find periodic orders.
I'm a little confused. In what energy ranges do you get into the nearly integrable setting, or you're not nearly integrable?
This is below 1. Sorry. So
like if you're really close to 0, or are you nearly integrable? Or
no, the mu can be whatever, but the energy has to be below 1. So
Or, I mean, are you going to make statements that are purely topological?
no.
All right.
I'm setting up the topology and the geometry first, and then I'm going to build on that.
Why are there only contact structures? It's like when you say equal, you lose the form.
The contact form is some contact form for that contact structure, whose ray vector field gives you the dynamics.
So you really wanted to make a statement about the forms,
Right. So exactly. So right now, all I'm saying is that this have contact structures, but moreover, the flow giving me the problem is actually a rate flow for some contact form for this standard contact.
I guess it won't be the Lugol form, because then we would be in very good shape.
No, it is a Lugol form, but it's a Lugol form restricted to some finite white star shaped domain.
Oh, sure. I guess you're rating that as a star S3.
Yeah.
Depends on how you view it.
Yeah, it's just that's sort of smoothly. Yeah. Okay, but then now we can try to use fancy tools. So that's sort of the message of this result. And I will be interested in trying to prove existence of periodic orbits. Okay, so that's
what I want to know.
yeah, that's my goal. Okay, I want some sort of Poincare-Birkhoff theorem. So the approach of Poincare to this exact problem for the planar case is the following. So he reduced it to the following 2 steps. So he first said, okay, let's say that you're able to find a global surface of section for the dynamics. So this is you have this 3-dimensional flow, which is a level set for the planar problem. And in there, I want to be able to find, say, an annulus whose boundary corresponds to periodic orbits, with the property that every other periodic orbit intersects the interior of the annulus in finite time in the future and in the past, transversely. Okay? So this is what's called a global surface of section. So it's like a section for the problem. I put my hand, and then everything sort of reduces to the dynamics of the corresponding return map. The return map is just I start with a point in the interior, follow the flow, and see where I come back. That's an error preserving map because the system is Hamiltonian. And now you want to. The second step is trying to find fixed point of periodic points for that return map, because by construction, periodic points of the return map are in 1-1 correspondence with periodic orbits of the original dynamics. So this changes a continuous dynamical system by a discrete dynamical system in one dimension less.
So in order to build this, he assumed something about mu.
Yeah, so Poincare first found this global surface of section in the integrable case, which is very easy. So here's write it down. And then he argued that it still persists when you perturb mu. Yeah, so that's what the interpretation that we have today. I mean, he of course didn't phrase this in these terms, but that's what we can get out of what he did. And so the second approach is a setting for the Poincare-Birkhoff theorem. So Poincare conjectured that, well, if my return map satisfies this twist condition, so it sort of twists one component of the boundary in one direction and the other one in the opposite direction, then you should have infinitely many periodic orbits of arbitrary large period. So the dynamics should be very rich. Of course, the counterexample always to have in mind is the irrational rotation, which doesn't satisfy the twist condition and doesn't have infinitely many orbits. No periodic orbits in the interior at all. And this is many people consider this to be the birth of symplectic topology for historical reasons that we can discuss later, like the Arnold conjecture for homology and things like this. So now the goal is to generalize this approach to the spatial problem. So what is a section? What is the Poincare-Birkhoff theorem for the return? Okay. So what is step one? So step one needs to introduce a notion of a global hypersurface of section, which will be the same thing, but in higher dimensions. And for this, let me introduce a notion of a Poincare decomposition. This is basically this will give us not just one section for the dynamics, but a family of. And the idea is, well, an open book decomposition on a manifold M is a fibration defined on the complement of some codimension 2 submanifold B, taking values in the circle. And I want that this fibration looks standard on some color neighborhood of B. So B, we assume that has trivial or normal bundles, so we can take color neighborhood trivializing it. And I want that this projection looks like the angle coordinates, some choice of polar coordinates in the normal directions. So the fibers of this projection of it, which are called the pages of the open book, look like in the picture like this. So basically, it looks like if you take a book and you open up the pages, so you see all of them having boundary on the binding of the open book, and then you glue the front cover to the back cover with some diffeomorphism, some gluing map. So that diffeomorphism is called the monogermy of the open book. So usually we say that M is the open book with page P and monogermy phi. So B is the binding, so the boundary of all the pages, and this monogermy is just a diffeomorphism.
I can open your book that you wrote.
So what? I mean, you should never go to if you go to Labyrinth's books, you should never try.
No, I'm just joking. Your book.
Right. I might, as I said, when I actually manage to publish it and get a physical copy, I'm going to try to glue it and send it to you. Anyways, so this is an open book decomposition. It seems like a strange thing to do at first, but it turns out it's a very general construction in the sense that every odd dimensional manifold, which is closed, can be presented in this way. So in particular, every 3 manifold has this presentation for some open book and some monodrome.
Monodrome of the floor.
Sorry?
Monodrome of the floor.
No. So right now there's no flow. So this is the monodrome is a topological object so far. It gives you the manifold. It's somewhat related to the flow, as I will explain, but you shouldn't think of it as a dynamical object.
These part of the data.
Right, it's part of the data that gives you the manifold. So now comes the flow. So now I have a smooth object, which is the open book, and I want to adapt it to some flow. So I have a flow dynamical system on M, and I will say that the open book is adapted to the dynamics of this flow if the binding of the open book is invariant, and the orbits which are away from the binding are transfers to the interior of all pages, and the return times I should add are finite in the future, are bounded towards the future and in the past. Okay? So you need to add some condition. Under that condition, each page of the open book, which is now a family of pages, becomes a global hypersurface of section. So this means it's codimension 1, the boundary is invariant, and the orbits away from the boundary make the interior of the pages transversely unbounded future and past time. Okay? So you have a circle family of choices for a section. So this is more than just one section. It really tells you that like the open book is somehow guiding the dynamical system. The dynamics is sort of wrapping around the binding. It cannot come back at any moment, right? So it's really sort of it gives you a bit more control in the dynamical system. In this situation, you can consider the associated Poincare return map. So you take any page, you take the interior, and then this map is defined according to the interior of each pages. And it's very subtle to check whether it extends to the boundary or not. It's sort of rather complicated. It usually has to deal with some sort of convexity. But anyways. So this is a theorem in this context that we proved with Otto already 5 years ago. And really time flies and it's very depressing and everything. So we proved the following. So we take the bounded regularized energy surface in the spatial C0-3BP. So really near the Earth and near the Moon or slightly past L1. And the result says that for any mu, then this compactified regularized level set can be presented as an open book decomposition where we understand the page and the monodromy very well. You know, this is an abstract statement, but the real statement is that this open book, we can find vibration of this abstract type, which is adapted to the dynamics. So the topology is, you know, the page is D stars 2, so unit disk cotangent bundle of S2, which is a 4 manifold. And the monodromy is the square root of what's called a densidal twist. So it's a symplectic morphism, it's part of a data giving you the manifold. There's a connected sum formula also for when you slightly pass L1. And the binding of this open books is always a planar problem. We knew from before that it's an invariant subset. Now we can realize it as a binding of some open book decomposition. So this, as before, reduces the dynamics to that of the return map. So now you can consider the return map, which is now a Hamiltonian map of D stars 2. I mean, I'm being a bit sloppy here when saying D stars 2. D stars 2 is the smooth type. You should really think of the page of the open book as a fiberwire star-shaped domain in S2. So the symplectic geometry of the page matters. But it's a Hamiltonian diffeomorphism of some fiberwire star-shaped domain in S2. And the interesting thing about this result is that it's non-perturbative. So I'm not perturbing mu. This mu can be whatever. It's arbitrary. So this is a very much non-perturbative result. And it's moreover explicit. Actually,
The epsilon depends on the mu.
The epsilon depends on mu, yeah. So the epsilon is the same epsilon as we had before. It's just the epsilon that gives you the contact condition. Maybe I should say, we also have a similar open books up to L2. This epsilon really doesn't matter, but then if we lose the contact condition, then the geometry is lost. So you don't have a contact structure supported by the open book anymore.
Ferrite starts.
Yeah, that's the hope for the planar part.
The pages are.
The pages are for manifolds, right? With boundary, boundary, the planar problem, but you should really think of them as fiberwire star-shaped domains in the S2. So the boundary depends on mu and C and so
what's very explicit?
F is not. I mean, the return map is explicit thing is the open book. So I can write down the vibration in coordinates. Of course, I cannot write down F. If I could write down F in coordinates, I would solve the three-body problem. So,
All right, so
now you have the return map, so now you're studying this map in dimension 4. So you managed to reduce the problem from dimension 5 to dimension 4. Okay, that's sort of the content of the theorem. So that sort of generalizes the first step, I would say completely. I mean, there's nothing more to say as far as I can see. You've found your reduction. And maybe I should emphasize that we don't know such a result for the planar problem. For the planar problem, we only know it up to certain convexity range of parameters. The results are very much, I mean, I wouldn't say perturbative, they're still non-perturbative to a certain extent, but they use holomorphic curves. Therefore, the open books that you get are they're very much non-explicit.
Are they open books or do you get finite, or you get finite energy affiliation?
No, you can get, so this is a result of Umberto with with Pedro and Wysotsky. So they get an actual open book with annually pages. So the same topology like this, but you replace S2 by S1. And this tau is just a square of the ranges. So the topology is, you kind of know what the topology of the open book for the planar problem should be. But finding it takes more technology than for the spatial problem. The spatial problem is like literally you sit down and write it down. It's not easy to do because it's very involved computations, but it doesn't require technology at all.
But what type of computation are you talking about?
Literally just write down a vibration and then check that the Hamiltonian vector field is transfers to the phase.
But how do you know that's corresponding to the whatever you want it to stay? Free body. Dynamics.
Because I start with the Hamiltonian vector field for that. I have to work with the vector field of the problem. I don't start with an arbitrary one. The reason, I can do that here because the planar problem is given, right? I know I have coordinates in which I can describe the invariant subset. For the planar problem itself, the invariant subset is a Hopf-link, so two orbits, which are the boundary of the annually of the Poincare annually, but those are not given to you. You have to find them, and for that, usually you have to change coordinates and do some crazy things. It's not easy to find an annuals closed surface section with boundary onto two orbits explicitly.
Binding there's some description.
The binding and for the planar problem.
No, for
This is a planar problem. The binding is the planar problem. It's really there. So you find a family of four manifolds with boundary exactly the planar problem.
And can you write down the Hamiltonian for the return? Like,
This is where, what do you know about it?
Okay, so the return map is Hamiltonian. I know that by abstract reasons, just abstractly I can prove that. But I don't know.
So, but how are you gonna use this then, just to prove something for arbitrary F or what?
I'm going to, under some condition of the boundary, the twist condition.
You will show it.
Yeah, and then what remains is to check the twist.
Can you show, maybe it is even related to that, can you show Hamiltonian is constant on the boundary?
Also no. So the thing is, you have a fixed map that you want to study, and you know it's Hamiltonian, but you don't have a fixed Hamiltonian generating it. You want to find the Hamiltonian with certain properties. And that's sort of a complicated part.
The return map is only defined.
That's true, but we're able to show that it extends to the bound.
Oh.
Finite.
Oh, I thought you made some choices or something.
I'm going to explain that now, actually. So the map extends to the boundary. I'll explain now whether continuously or not in a second. Okay? So that's sort of the key. That's key for what comes now.
Didn't you ever see zero in that? That's
Yeah.
okay.
Okay, so
See one out of the
So here's the C0, here's the zero of the title. So unfortunately, in the setup, there's a trade-off. First of all, it's basically like a coordinate description of the setup. In one coordinate description of the setup, the return map extends smoothly to the boundary. We can actually prove that. But the symplectic form degenerates at the boundary. Because the vector field, the red vector field is tangent to the boundary. So you have a degeneration of very specific, of a very specific type. Or the second, you can actually choose to fix that. There's a way to make the symplectic form actually symplectic along the boundary, but the price that you pay is that the return map extends only continuously to the boundary. Okay. So either your geometry is nice or your dynamics is nice, but not both. So that's sort of
Why do you want to extend it?
well,
That's the problem, curves should extend.
it's good to know that it extends for several reasons. It's the Floer homology.
I understand, but an exhaustion.
Yeah, that's basically what I will be going to do. Not in the way that you're thinking, but in a different way. Anyway, so this is a problem. So in what follows, first of all, the two setups are equivalent. They're related by some change of coordinates. So the change of coordinates conjugation, which I call square root map, suggestively, is only smooth in the interior but continuous at the boundary. you should really think like literally the square root. Square root is continuous at the bound at 0, but not smooth at 0. And then what follows, I will choose the setup of B. Okay, well, I will choose my symplectic form to be nice, but my dynamics to be only C0 at the bound. And then I'll have to deal with that somehow. Okay, so remark, sort of this trade-off also holds for classical and symplectic billiards. So if you ever studied billiards in your life or ever looked at them, they're described by billiard maps, and the billiard maps also have this trade-off. So it's a fact of life that you can't get rid of. It's a feature of a setup, and you cannot go around it. Okay, so in this context, in B, remember now we'll introduce the class of maps that I will study, my hope is that the return map of the three-body problem will fall in this class, but it's something that we have to check. So you take the definition is as follows. So you take a map on some Liouville domain. Now the page of the open book in setup B becomes a Liouville domain. And I have a map, I will consider a contact form at the boundary, which you think of as a contact form for the planar problem. We say that F is a C0-Hamiltonian twist map if the following conditions hold. So first, I want this map to be generated by a C1. Actually, I need C2 actually. I want to be able to C2 Hamiltonian in the interior. So the map is Hamiltonian in this sense, a priori. Extension, I want that both the map and the Hamiltonian with C0 extension to the boundary, but not necessarily C1 extensions. So this is the C0 part. And it comes from the setup. And the condition, the last condition, which is a crucial one, which I'm calling the weakened twist condition, because before I had a stronger twist condition, but every time I will say twist condition today means a weakened twist condition. I just want to ask that at the boundary or near the boundary, the generated Hamiltonian satisfies the following. So if I evaluate the contact form at the boundary on the Hamiltonian vector field, I get a function which might probably depends on time. And I want it to be, first of all, positive, strictly positive. And as I approach the boundary, I want it to explode to infinity, okay? Monotonically to infinity. So intuitively, this is measuring how transverse the vector field is with respect to the contact structure. And what I want is that as you go to the boundary, this transversality explodes to infinity. It's like an infinite twist map. It's like you're twisted infinitely off. Okay, so that's sort of what I will call this.
So it generalizes the twist condition for the annulus because the right vector field on the annulus points one way on the top boundary and the other way on the bottom boundary. And you're seeing the Hamiltonian vector field.
This is a generalization of a classical twist condition in this setup, because pointing positively with respect to the contact structure on the circle just means moving in the positive direction given by the orientation. And the orientations of the two boundary components are opposite. So positive in both of them means opposite motion, twist condition. But if you actually work in this setup, I mean, the problem when you're doing dynamics on surfaces, everything is topologically. People study this homomorphisms, right? So you don't really see the subtleties which we encounter in the Hamiltonian version of the setup. You wouldn't see the degeneracy of the boundary or the C0 at the boundary because everything is a homomorph. But in the setup, the subtleties arise quite crucially. Okay, so that's the definition and the theorem. And this is what I want to. The main sort of point of today is present this result. So this is we did this with Arthur Limoges, who's my student now at Heidelberg, who's just graduating in December. And this is based on a previous result of mine with Otto. Basically, we improved our previous result quite a bit. The statement is the following. So you take a C0-Hamiltonian twist map on a Liouville domain, and you assume three conditions. The first condition is not really an assumption. You assume that all fixed points of F are isolated. That means finitely many. If that doesn't hold, then you already found infinitely many fixed points. Okay? The second condition is something about the manifold, just C1 equals 0 if dimension is at least 4. That has to do with the grading in symplectic cohomology. So this is a condition that is always satisfied for cotangent bundles of orientable manifolds. So it's not really a strong condition at all. And the third condition, which is also not a very strong condition, assumes that the symplectic homology is non-zero in infinitely many degrees. Okay, cotangent bundles of spheres satisfy that condition. So for S2, which is the case that we care about for the three-body problem, is also already satisfied. And then the conclusion is the same as in Poincare-Birkhoff. So the conclusion that F has simple interior periodic points of arbitrarily large minimal period. Well, simple here and minimal are redundant, but so you want that you're not always finding iterations of the same points. Okay, so the crucial all of these three conditions are not you know.
You have a lower bound for the number?
Well, infinitely many, right?
Yeah, but you can ask how many of the period come.
If you fix a period, yeah.
That grows with X, yeah.
Yeah, so that would be the next thing. First of all, if you can prescribe the period, which you can in the planar
I
case.
mean, I understand you've lost the time period.
Yeah.
But just in the section.
Yeah, I don't know. I would like to say, give some sort of statement about the ratio, about the rate of
Right,
of growth.
how about? Just
At the start, didn't Poincare and Birkhoff only get like 2 fixed points or something?
Yeah, so the original result was stated, there's at least 2 fixed points.
Yeah.
And then somebody else, I forget who, as a
That
clever
was
trick.
Frank's, right?
Frank's maybe, but it's a very simple trick to get this statement out of the original one.
Oh,
Just
okay.
by doing some covering tricks.
Yeah. That's sort of the closed geodesics.
Yeah,
Oh.
exactly. Maybe it holds, my suspicion is that the same result that for geodesics, you know, it goes as a number of primes.
Yeah.
That should also hold. And
I think Nancy Higgs in that case gave a lower,
yeah,
combining the two.
yeah, so log of whatever divided.
But she had some elementary number theory problem that she registered things.
I wouldn't know myself how to attack that problem in this setup, but I haven't thought about this. Anyway, so we also have a version of Hamiltonian chords between Lagrangians. So you study now, you put a Lagrangian or 2 Lagrangians and you study how many.
Wait a minute, so these assumptions which you're saying are not important. Why haven't you got rid of them?
Well, because this is for arbitrary liberal domains. I will now give you a special case.
Okay.
So they're not important for the three-body problem because the W is very specific.
They apply, they all apply.
They'll apply, except the only obstruction is the twist condition.
Okay.
And just one comment. So okay, we have a version for Lagrangians. Maybe this is for X-verse, replace the symplectic homology by Raffer homology. And then we expect the third condition, this sort of infinitely many degrees non-zero, just can be relaxed to non-zero symplectic homology, which looks much better on the nose, but conjecturally they're the same. Okay? But we don't know. Anyways, this is just a remark. But as I said, for the three-body problem, this condition holds. So this is okay. Let me mention it. Yes, here. Let me mention the special case. The remark is that the C1 of T star Q for orientable Q is 0. So the second condition is satisfied. The symplectic homology of a cotangent bundle is well known to be the homology of the loop space. So this is infinite dimensional. So the special case is for fiber-wise star-shaped domains and T star Sn. If you have a Hamiltonian twist map and descends on such a domain, then the conclusion holds. It has periodic orbits of arbitrary large minimal. So this is the three-body problem is corresponding n equals 2. So you see like the only remaining obstruction in this setup is the twist condition. And let me also mention a comparison to my previous result with Otto. So the twist condition before was more rigid. So we asked that the Hamiltonian vector field should point in the right direction at the boundary, which is not an open condition. Now I'm just asking that is pointing positively with respect to the contact structure. So pointing in the upper half space at the tangent space. So that's a C1 open condition. The boundary degeneracy is addressed. So this trade-off that I alluded to before, which drove me crazy for a long time, but now actually I managed to sort of work around. So the previous result didn't address this, we address it now explicitly. And this is going well more to the how we prove it, which I will mention now, but now what I want is to find interior periodic orbits, because boundary periodic orbits are the planar orbits, and the interior ones are the spatial orbits. So I want to push everything up from the boundary to the interior, and that's a very sort of subtle thing to do. You need to have some sort of mechanism to tell the difference between boundary and interior. And the mechanism in the context of fluid homology is either action or index growth. So before that, before in the previous result, we used index growth. We proved basically that under some condition, the index of all the boundary orbits shoots off to infinity. So when you compute symplectic homology in a limit by iterating your map, it doesn't appear. So all the generators come from the interior. In this case, we're replacing index by action. So what we prove is that the action of all the boundary orbits goes to infinity. Therefore, they also do not contribute to the computation of symplectic homology in the limit. So everything that sort of can contribute to the symplectic homology has to come from the interior. Okay, so that's sort of anyways, this is a bit technical, but
So in comparison to what Birkhoff and maybe Frank's the special case.
Yeah.
There is a theorem there, what's based on like also with a twist condition.
right, I mean, okay. The thing about Frank's is that there's no twist condition, right? It's either 0 or infinitely many in the interior. And he uses this notion of a rotation set or rotation vectors and whatnot. But you don't have that here because there's no first
In that case, they know more. In that case, they don't have to put the twist condition.
Exactly, there's no twist condition in Frank's. But we cannot use that.
Because I was wondering if you recover their result.
No,
With the twist condition, you do that.
right, yeah. If you add the twist condition, that's Poincare-Birkhoff.
Okay, that's what I was trying to.
Yeah.
So then your proof is a new proof of their result.
Also Poincare-Birkhoff, yeah, in the Hamiltonian setting. Because remember, they do everything for homeomorphisms, which I cannot do in this generality. And probably I don't think it's possible at all. For example, the Brouwer fixed point theorem doesn't hold anymore for Hamiltonian maps in the interior of a ball.
So maybe this type of setting should work, like coming from open book, because it's like very particular that it's
I
constructed.
don't know. You could ask the opposite question. If you give me a Hamiltonian map on a page, can I realize that it's a return map for some contact form? I know how to do that under the old twist condition. Okay. Anyways, so this is a special case which gives you a feeling of how general the result actually is. And this now let me mention a bit. How much chapter?
It's 5:23.
8 minutes. Okay. I'll mention maybe a bit of there's 3 steps to the proof. Okay. And I'll try to give you a sort of at least a feel of how you go about proving this result. So the first thing to do is to deal with the degeneracy at the boundary, or in other words, the C0-ness. So you want to somehow smoothen out your map, and then prove that that in some limit, then when you take the smoothening to go closer to the boundary, you get rid of everything near the boundary. So the idea is you take your C0-Hamiltonian twist map F, which is generated by some Hamiltonian H in the interior. And I want to be able to express it as the limit of C1 Hamiltonian twist maps. So generated by Hamiltonians, which depend on some smoothening parameter epsilon. And these Hamiltonians are actually C1. And what I want is that these functions, which measure how transfers to the contact structure we are at the boundary, they're positive, but they're finite for positive epsilon. And when epsilon goes to 0, I want that this expression here explodes to infinity, while all other derivatives of this function stay bounded. So the idea is, intuitively, I start with a Hamiltonian twist map, which twists infinitely many times as I go to the boundary. I want to express that as a limit of twisting a lot, but a finite amount of time. So, but twisting a lot more and more and more. Okay, so this is what the epsilon is doing. You should think that as the twisting amount is 1 over epsilon. So where epsilon goes to 0, it's just shoots off to infinity.
Does the twisting help tell you anything about the location of the orbit safely? I mean,
Yeah, so
the standard example, if you take an infinite twist, all the
Exactly.
high period orbits are near the bottom.
what's happening is, and we'll see it now, is that all the periodic orbits are being pushed into. So that's
Okay, where they to do the enduring.
With this epsilon parameter. So it's kind of, that's the key point.
Yeah, I guess my question was very slightly different. It was that, you should get, the final result gives you periodic orbits of unbounded period. I was wondering if you can say that, I have a sequence of periodic orbits with unbounded minimal period that approach the boundary or.
You could, but in this generality, you don't. I don't think you can say anything about that. Okay, this is how you deal with the C0 thing. Now you replace it by C1 maps, and they approximate your original map when epsilon goes to 0. Okay, so that's sort of the first thing. And now we extend this Hamiltonians for positive epsilon to the completion. So the completion is you just add the cylindrical end to W, so to the Liouville domain. Now it's just into a Liouville manifold, right? It's a non-compact manifold. And I want to extend it, my Hamiltonian to some new Hamiltonian, which is admissible for symplectic homology. That means that it's linear, sufficient, it's linear in the cylindrical end, and the slope is not a period of a ring orbit at the bound. So this is sort of a standard thing to do. So now this thing is well defined. I can compute the Fourier homology of this. And now the key point is that because of this explosion, when I take the limit of epsilon going to 0, the slopes of this Hamiltonian goes off to infinity. Therefore, when I take the limit, I compute symplectic homology. So this is how you connect the dynamics that you care about with the symplectic geometry of the manifold. Okay. And the third point is, and this is what I was saying too before, which was maybe a bit cryptic, but now hopefully is a bit more clear. In a priori, the generators of symplectic homology coming from this Fourier homologies come from the boundary, or from this artificial extension that I did. I added a color neighborhood of new orbits, which are completely artificial, and we should get rid of. And this is what the third step does for you. Under this assumption, so A and B, which I will call the quantitative twist condition, if the first derivative of the Hamiltonian in the Liouville direction, the minimum of that along the boundary is greater than the max of the Hamiltonian itself, so a C1 quantity being greater than a C0 quantity, so this is like sort of gap, which of course implies the twist condition that I had before because of assumption A, that the Hamiltonian is positive itself. If you have this, then you can prove that the Hamiltonian action of orbits at the boundary shoots off to minus infinity with period. So the longer the period, the larger in absolute value the action of the orbit at the boundary. So that tells you that those orbits cannot contribute to the limit to the symplectic homology because they escape the actual filtration. Like you have an actual filtration symplectic homology. So all the contributions to symplectic homology from these Floer groups come from the interior. So that's sort of the key. And then you put in together these 3 steps, you can prove the theorem as follows. So the end of the proof is the following. So you say, okay, first of all, let's observe that let's observe this condition here. Because this derivatives are exploding with epsilon, while all other derivatives stay bounded, if I wait long enough, so if epsilon is sufficiently small, then this condition is automatically satisfied. So this is exploding to infinity, this stays bounded with epsilon. Okay, so the weakened twist condition implies a quantitative twist condition for free. So that's the first observation. So this is not really a condition anymore if you assume the twist condition. So no contributions from the boundary orbits of the Fourier homology contribute to the symplectic homology. So the generators are all interior. So that's sort of the key point in here. And the theorem the proof finishes as follows. So okay, let's assume that we've had finitely many periodic points by contradiction. they have some periods M1 up to Mn, and gamma 1 up to k denote the finite many fixed points, which are also some, we have finite many of them. So there's k fixed points and n periodic points. Now you take a bunch of primes going to infinity, and you consider epsilon as just the inverse of those primes. And the primes are large enough that they're greater than the max of this periods. So now the point is now.
You need for Liberty front. You made my day.
That's true. Yeah, I guess I didn't even think about it. So now the point is now that you have well-defined Floer homology groups for the pith iterates of the Hamiltonian, but where you also smoothen at the same time. So I'm iterating the Hamiltonian and I'm smoothing it out at the same time, where the parameter now is this prime. Okay, so the larger the prime, the smaller the epsilon, and the greater the period of the orbits. And in the limit, because of the steps before, they compute symplectic homology. And now you say, okay, we're assuming that the symplectic homology is supported in infinitely many degrees. Okay, so let's take some large n, which is bigger than the dimension of the manifold times k. K is a number of fixed points. And I'll take n degrees such that the symplectic homology is non-zero in those degrees. And now I say, because of this, if I put I sub j here, what I see is that the corresponding Floer group is non-zero for large I. So this I sub j group for this Hamiltonian here is non-zero for I sufficiently large and for every j from 1 to n. And now, but you look at what could possibly be the generators of this Floer group. So the pi's are prime, therefore the periods of the xj's do not divide the primes, and therefore this xj's cannot contribute to this Floer group. There's no way because the generators of this Floer group are pith orbits of the Hamiltonian. So the only thing that can contribute to this Floer group are generators of the form gamma j to the pi, so pith iterates of the one periodic orbits. But now, let's assume for simplicity that these are non-degenerate. Therefore, they have the associated degree, the Collins-Ender index. But now there's k such generators, so they can cover at most k degrees. But this is a contradiction because I took n to be greater than k. And there's more degrees to cover than degrees that could be possibly covered from this orbits. And now in the general case where this could be the general priori, the key point is the use of local Floer homology. So this is something that Ginzburg taught us how to do. At least I learned from Ginzburg's papers on how to do this. The point is, if you have a degenerate orbit, you can perturb the Hamiltonian slightly, and it bifurcates into a finite number of non-degenerate orbits. And then you look at the corresponding degrees of those orbits. It turns out that the degrees that can come out of a single orbit can cover at most 2n degrees. So 2n is the dimension of the manifold. This has to do with the mean index. The mean index of all of these Collins-Ender index are in a window of size 2n around the mean index of the general periodic form. Okay, so they can only cover 2n, but now I took my big N, remember, to be bigger than the dimension of the manifold times k. I still get a contribution. That's the end. Think.
So there's Elon Musk one periodic orbits. Now, is that what they need? Are the periodic orbits important for them?
Yeah, but
Is that what they want to have these satellites going?
They do something even more interesting. They do choreography. So they have a bunch of satellites, and they want them to move in a choreography. So like the distances between them needs to be fixed. So they're always covering internet. Yeah.
Why can't your method be used numerically? You said it's hopeless to write down.
I wouldn't know how to. I mean, you need to check this twist condition, right?
Yeah, of course.
And so, as I said, the time one map is fixed, but the Hamiltonian is not. I know that the map is Hamiltonian, but integrating Hamiltonian map is not something that I don't know how to do that.
I'm saying if somebody was trying to use your theory, these coordinates, they can probably integrate that.
No, that's for sure. So actually, I'm doing that with some engineers.
Yeah.
So visualizing the return map numerically, that's something that you can do. But not this fixed.
No, not for a theory, but I'm just curious.
Yeah,
I know that after Poincare, periodic orbits is what everybody wants, but I'm asking, I'm trying to understand. what
yeah.
they want.
So in because the open book is explicit, you can fix a section, you can just coordinates, and you can integrate the equations and then try to visualize the map. But now it's a four-dimensional thing, so you have to be clever how you project and things like this. But they do it, engineers. I've seen plenty of talks of people doing four-dimensional Poincare maps in the astrodynamics community. So I've been talking to some of those people, and a student of Shane Ross, which is a colleague, astrodynamicist, and I forget what he is, but one of his students is doing this numerical work, and hopefully, I don't know, at least it gives us some idea of what to find, what is out there.
Thank Augustine.